timely before we move into integration and take off from there. Now that we looked at most of the functions, the types of functions we're going to end up differentiating, I thought maybe a little summary was in order. And so before I dive into that, I just want to go over something fundamental to a lot of the differentiation we do, and something that maybe I didn't make clear enough, so I'm trying to address that now, and that is the chain rule. Now the chain rule says that I can find dy dx, but I can go through a third party if you like. That third party, it can be a du, or it could be a dm, or it doesn't really have to be a du. But what, in effect, if you think about what I've just written there in blue, cancelling out, although it's not strictly how it works, but you think about, those cancel each other out. We're left with dy dx in black, and that's what we use. We use it's called the chain rule. It means that when we've got composite functions, we can run a substitution of u through, and we can derive through a secondary function. Now that underpins so many of the differentiation rules. So I thought it was worth just looking at and maybe just do one example of. So an example of that is any function at all. So let's take x squared plus 1 to the power of 7. Okay, and look at differentiating this, but we're going to do it through a substitution. So u is going to equal x squared plus 1, and this allows us therefore to rewrite. So this should say y equals. Okay, then it allows us to rewrite this as y equals u to the power of 7. U to the power of 7, rather than x squared plus 1 to the power of 7, because we know how to differentiate that. We can just use what we know of differentiation to say, well, that's 7u to the power of 6. Okay, but that's dy du, not dy dx. My apologies. That needs to be a dy du, right? But we're after dy dx. So let's go back up here. I've got dy du. I've got this bit here. I need a du dx. The du dx is coming out of this, isn't it? Out of our substitution. So du dx is equal to 2x. So my dy dx is going to be this dy du by this du dx. So that's why we end up with multiplying always by the derivative of the function. In this case, it's the x squared plus 1. If we're taking sine of 4x, that's why we multiply by the derivative of 4x, or 4, and we'll look at that in a moment. But so to finish this one off, we can therefore say that dy dx is equal to dy du, which is this 7u to the power of 6, by du dx, which is 2x. So dy dx is being sorted out. It's 14x u to the x, but now the last step is to just take the u back out and write it as 14x x squared plus 1 to the power of 6. Now when we do this, we don't go through all this process. We remember the chain rule and we go, no, forget that. I'm straight into it. I'm over here. I'm taking the 7 down. My x squared plus 1 holds. I reduce the power by 1, and then I multiply by 2x. And then I put the 7 and the 2x together to simplify to get 14x x squared plus 1 to the power of 6. All right, so the same thing. This justifies it. Now, the chain rule is used in order to show that when I have y equals, I was saying a minute ago, sine 4x, I write that my dy dx is sine to cos 4x stays, and then I multiply by 4, so I get 4 cos 4x. Now that's because we let u equal this, u equal 4x. So our du dx is equal to 4. We then get y equals sine u, so my dy du is cos u, so I end up with cos u times 4, or 4 cos u. Subbing u equals 4x back in, we get 4 cos 4x. That happens with all our differentiation rules. So let's have a look now at our rules of differentiation. So if we've got, we'll have a y list and a y dash list. So when I've got f of x all to the power of n, Then I've got n f dash x, f of x to the power of n minus 1. Okay, when I've got, what else have we done? We've done e to the power of fx. My derivative is f dash x, e to the function of x. That's a bit messy. Fix that up. F dash x, e to the fx. See the pattern here. When I've got ln fx, that's f dash x by 1 on fx, which is more easily written as just f dash x over fx. Okay, so that's my log function, exponential, my polynomial. Then we go into sine f dash x. Sine goes to cos, fx holds. Cos fx, f dash x, it's minus, isn't it? Sine fx. So cos goes to minus sine. And for tan fx, we've got f dash x by 1 over cos squared fx, or f dash x sec squared fx. Alright, so that gives us a full rundown on all the differentiation we've done so far. And as we move next into integration, we're going to be going back the other way. We're going to be taking functions and recognizing and doing the reverse process in order to find a function's original, or its integral, as we call it. So that's the next step, but that sort of summarizes where we're up to at the moment. Okay, cheers.